Right, okay, question 7, and this is all to do with logic gates. Complete the truth table for the OR gate. Now remember, OR requires either or input to be a 1 in order for a 1 to be output. So here we don't have any 1s at all, so that output is a 0. Either or of these is a 1? Yes, it is. Either of these is a 1? Yes, it is. Either of these is a 1? Yes, it is. Complete the truth table for the logic circuit shown in figure 6. So notice we've got all the different possibilities of the inputs. So 0, 0. So what happens if both of these are 0? So A is 0, B is 0. Well, this is going all the way along to here. So this input to inside here would be a 0. So that, imagine it's just electricity going along here. There's no electricity flowing along here because it's a 0. No electricity here. There's no electricity there or here. And requires both inputs to be 1 in order for the output to be 1. So that's 0. So this is going to be traveling to 0 here. Again, this AND needs both zeros. And then this is a NOT gate. So it NOTs the input. So the output here is 0 at the start, goes through this and NOTs the 0 and gets a 1. So what is X, Y, and Z? So X was a 0. Y was a 0, Z was a 1. What about A is 0 and B is 1? Let's have a look at that. So if A and B are both 1s, there's a 1 that flows through here. This electricity, Y, goes all the way through here. There's electricity flying up to there. There's no electricity here. So we've got 0 and 1 here. And this is an AND. Well, both of these need to be a 1. AND requires both inputs, this one and this one, to be a 1. So this is a 0. So X is a 0. And so we've got a 0 here. AND requires both of these to be a 1. They're not. Then one of them is a 0. So this is also a 0. And it NOTs this 0 now to be a 1. So this is going to be a 1. Let's go to the next bit now. Now it's got A as 1 and B as 0. So there's a 1 here. There's a 0 there. This 0 goes all the way along to here. 1 and 0, that's 0. So X is 0. There's a 0 here. 0 and 0 is also 0. So there's a 1. This is 0. And it NOTs this to be a Z. So be a 1. So that's a 1. Because it NOTs this 0 to be a 1. And then finally, we've got a 1 and a 1. So we've got a 1 here, a 1 here. That 1 will go all the way to there. This 1 will come up here. This will be a 1 from here. 1 and 1. Well, both are 1s, so we need both of those to be 1s for the output to be a 1. So that's a 1. So X is 1. Therefore, there's a 1 here. There's a 1 and a 1 going into, coming out of here. A 1 and 1 is also 1. So Y will be 1. And then it will NOT this to be a 0. Okay, a logic circuit is being developed for an automatic door system. The automatic door has two sensors, one on either side of the door, sensor F and sensor B. So, okay, either side of the door. So this is before the door and this is after the door. The door opens when either, what does either mean? Either is either or, which is, that's like an or here. Of these sensors is activated. So we need an OR gate connecting these. The door system can also be turned on using a manual switch S. The door will not open unless S is on. Unless S is on. So it will not open. This will not be a 1 here, this D for door, unless this is on. Okay, so this must be on. And okay, the output from this logic circuit for whether the door is open or not is D. Complete the logic circuit. So this needs to be on, or, so if this is on, then the output will be on. If either of these is on, then the output will depend on those. So let's just go through this again. So basically what we need to do is, it says the door system can also be turned on or off using a manual switch. Okay, so the manual switch, the door will not open unless this is on. This must be on. So this therefore must be an AND gate. So that's an AND gate. So this is AND and this one is OR. So either of these must be on, but this switch certainly must be on. Okay, so these must be both ANDed in order to be on.